is statistical measures. So this is stats. Okay, so there are lots of words that you will use in statistics. So we're going to talk about those words now. So the first thing is a random sample. So a random sample would be if all members of a population have an equal chance of being in the sample. Okay, so I could do a random sample around Indianapolis. I could walk around, I could ask people different survey questions, right? But it's not really a random sample if you say, okay, in this classroom, I'm only going to ask the boys a question. Or if I'm going to go to the mall and I'm going to ask people questions, but it's only going to be students or people that walk out of Abercrombie. Right? That's not really a random sample of the population. Does that make sense? It's a random sample of people that go to Abercrombie, yes, but no, it wouldn't be a random sample of an entire population. Okay? So data can be divided into two types. The two types are quantitative and qualitative. So you will first have a quantity. And if you have a quantity, that quantity is going to break into what we call discrete or continuous data. But if you don't have a quantity, you will probably have a quality, so qualitative. So quantities, we know, are numbers, so these are going to break into like, you know, numerical data, like maybe your shoe size or how tall you are or something. That would be quantitative data. And qualitative is going to be things like this person is a conservative, a liberal, a moderate, or this person has blue eyes or brown eyes, and so on. Does that make sense? So based on a quality that they have. So if you get that something is qualitative, we do not break it down into discrete and continuous. That is only for the quantitative one. Okay, so when we talk about discrete and continuous, okay, I just mentioned shoe size, so let's talk about that. If I talk about your shoe size, that is something that is discrete. There is a set number difference between each shoe size, right? So you could be like an 8, you could be an 8.5, a 9, a 9.5, a 10, right? You cannot be a 9.25. Does that make sense? Your foot may be a 9.25, but you would have to select between one of those two things. Okay, so that would be a quantitative data, but it would be discrete, would be shoe sizes, okay? But your foot size is continuous. Do you understand what I mean by that? Okay, the size of your foot is not a set size 8 or size 8.5. Your foot could be 8.1235. I don't know what units we would use for that. Inches, probably not inches, but whatever it is they use for shoe sizes. Does this make sense? I think it is supposed to be inches, but it's not really inches. All right, anyway, so that would be something that is continuous, where there's not like a set difference between the sizes. Okay, so if I take a measurement of your foot, it could be a little bit bigger. All right, so what are some other examples of discrete and continuous? Can you guys think of any examples? They don't like the squeaking over there. What? Shoe sizes. Shoe sizes. We just did that. What else?
Shirt sizes.
Shirt sizes. Get off the sizes. What else could we do? Levels of floors. You can't have 1.5 for your floor. But the distance that the elevator goes could be a continuous. Height would be, what do you think? Height would be continuous, but if I was saying, oh, you have to measure your height in feet and inches, then it would be discrete, right? Because it'd be a set, like you would have to round to whatever inch. Does that make sense? But our heights are really continuous. It's like a little bit more, or a little bit less than that measurement. Okay, so those are some good examples. All right, so number 1, so identify the data as either qualitative or quantitative. If it's quantitative, then break it into either discrete or continuous. So number 1, the number of questions answered correctly on a true-false test. Is it a quantity or a quality? Quantity, so it's quantitative. Is it discrete or continuous? It is discrete. So as much as I would like to grade and give you like 1.25167 points out of 3, right, I don't do that, right? I give you like 1 out of 3, 2 out of 3. I don't ever do anything out of 3. Who am I kidding? Okay, so how about the next one? So the weight of each animal in a zoo. Quantity or quality? Quantity, right? Is it discrete or continuous? It's continuous. What if I phrased it differently? And I said the weight that shows up on a scale of every animal in the zoo. That would be discrete, because if it's showing up on a scale, I don't know about your scales at home. My scale does like a decimal point pass, so it might say 200.2 pounds. right? That's giving me one little decimal point, but it is that little difference, right? It's 200.2, 200.3. I can measure that distance. So that's going to be a discrete amount then. All right, so a person's blood type, what do we think? Qualitative. All right, it's just a quality that they have. It is not measurable. You can't have a number associated with it. All right, so the frequency of an element is the number of times a particular value occurs. The relative frequency relates it back to the original number, the amount of people in the survey. So here's an example of one, a very easy one. So it says a class of 25 students took a math test. 4 people earned A's, 11 people earned B's, 7 people earned C's, and 3 people earned F's. Whoops, no D's. Jeez, I'm struggling. Okay, 3 people earned F's. The fact that we don't have D's is really bothering me, apparently, in this problem. All right, so saying that 4 people got A's, if you don't know how many people are in the class, it's not really giving you any information. If I'm like, oh yeah, 4 people got A's on that last test, you'd be like, well, how many people took the test? Was it only 5 people? Because that's good. If your students, if 4 of them got A's and there were only 5 people total, that's good. But if I'm like, oh yeah, I have 500 students, that would be terrible. That would be the worst test ever. Only 4 people got A's, you would need to curve that, right? So that's why we consider relative frequency. Yes. Nobody studied, so it wasn't my fault. All right, so the relative frequency was 4 over 25, 11 out of 25, 7 over 25, and 3 over 25. It relates it back to the original group number, how many people were in the group. And you can do things with this data, like you could make a bar graph. Do you guys remember bar graphs from elementary school? And you could say maybe 5 and 10. And you could say, oh, the first one was 4 people. The next one was 11 people, so up a little bit more than 10. And then we had 7 people. And then we had 3 people. So you can make a little bar graph. And you could discuss the shape of the bar graph. So in this case, it's tall in the middle of it. That's good when things are tall in the middle. That means most people are kind of getting that average score. In this case, it's pretty good because a lot of people are getting B's. The most is at B. It's not at C or F, right? So this shape kind of goes up, and then it comes back down. But it might be shifted over a little bit. It's more towards the B's than the C's. So it might be shifted a little bit, okay? So we have these different shapes, and these are the 4 common shapes that we will talk about. The first one is the uniform distribution shape. So this is when all data values have approximately the same frequency. So it's when it's straight across. All of them have pretty much the same height. It doesn't have to be perfect. You could have some that were up, a little bit down, a little bit up, a little bit down. I mean, as long as they're somewhat close. It could be a little jagged. All right, symmetric. This is a very common one that you will see. This involves the bell curve. Have you guys heard of the bell curve before? We'll be talking about this in the next section, 12.5. What do you mean the other way?
Like go down the middle.
Yeah, good. So you could have anything that is symmetric. So it says the right and left sides of the distribution have frequencies that are mirror images. So you could do something like this. This would also be symmetric. It's a very weird distribution, but it could happen. Or it could go down in the middle. All right, skewed right. This is what I think is really dumb in statistics. Skewed right looks like this. Skewed left looks like this. Isn't that dumb? You're talking about the tail. The tail is on the right. And skewed left, the tail is on left. Okay, so I think it's dumb. I would call the first one skewed left because it looks like it's more on the left than it is on the right. Okay, so it's kind of backwards of what you would think because we're talking about the tail. Okay, so let's talk about some different distribution shapes. So the very first one, it says, from the 4 common distribution shapes, choose the best one. So A, the ages of people in an elementary school during a typical school day, including the faculty and staff. So all the little kids and the faculty, what do you think the distribution shape would be? It's going to be like that. It is skewed right. Because if I was doing like a little, you don't have to draw this, but if I was doing a little chart and I was like, oh, how many 4-year-olds, 5-year-olds, 6-year-olds, 7, 8, 9, 10, and so on. There would be a whole bunch in this area. And then the heights of these ones, when I talk about 18-year-olds, 19-year-olds, 20-year-olds, there's not very many, right? There might be some that are pretty close to retirement, but the bulk of your data is on the left, so we call that skewed right. Does that make sense? All right, the age of death for all people in the United States. Skewed left, that's correct. So most people die when they're older. So if they're 75, 80, 90, right, that's when they're dying, okay? But there are some people that still die young, but they're not like the bulk of the population, right? The bulk of the population would be later, so it's going to be skewed left. All right, C, the day of the week of all students' birthdays in a school, where Sunday is 1, Monday is 2, and so on. What do you think? It'd be uniform. It's actually not in real life, isn't that weird? It's mostly uniform, I guess, but there's the most people are born on Mondays. Isn't that weird? Do you know why?
Because something to do with it.
Why would most people be born? Usually, like there's a lot of well, I don't know. So let's say you go on a weekend trip as a doctor with your family. You're spending time with your family. Would you schedule someone to be induced on Saturday? No. Nobody gets induced on the weekend. Like, it's very rare to get induced on the weekend. So most of them are on Monday, right when they come back. Induced, like you start labor. Yeah, but there's also, like, sometimes, the other class was amazed by this, they're like, what do they say? Just, like, stop having the baby? And they do, in a way. Like, with both of my boys, I started labor on Friday, and I had one of them on Sunday, and I had one of them on Saturday, because they sent me home. Like, I went to the hospital, and they were like, oh, you can wait this out at home a little bit. I'm like, I'm having contractions. Like, please just take the baby out of me. So, yeah, so most of them were born on Monday. Weird, huh? All right, anyway, so the IQ scores of all the men living in the United States. It's symmetric. This would be the bell curve, because most people are kind of average intelligence, but there are some people that are way over here. These are what we call outliers. So this would be an outlier too. Okay, so people that are super, super bright, people that are not super, super bright. Okay, outliers. Okay, so outliers are really important. I have a friend who, she was an optometrist, and she decided to go back to school because she wanted to be a doctor of optometry, which would allow, well, she was already a doctor of optometry, a PhD. She wanted her PhD in optometry so she could teach at the college level, and she had to write a thesis. And she was writing a thesis about kids and certain, like, babies, little kids, babies and small children, and something in their eye, but she had so many people that were outliers for her thesis, like she thought something was true, and there were so many people that went against the rule that she had to throw out her entire thesis. So outliers are important. So you can have one or two, a few outliers, but if you start to get a whole bunch of outliers, then your data is not good. All right, so the next one. So it says a supermarket manager wants to know how long customers are waiting in the express lane. A random sample of 15 customers is taken, informing wait time in minutes. Create a stem plot of the data below and discuss its shape. So a stem plot is going to look, if there's a straight line, and if I had numbers like 35, 47, 48, 32, when we create the stem plot, we would have 32, but we'd also have 35, so we write it like that, 32 and 35. 47, but also 48, okay? So you just do the first digit, and the second digit is on the other side. So we have this with a decimal, so that's fine. The first one, like the smallest starts out with 0, the biggest starts out with 3. I don't know what the biggest is, 3.4 maybe? So we're going to go 0, 1, 2, and 3. And I'm going to go through in order, and I'm going to write as many as possible. Well, I'm going to write all of them. Sorry, 3.1, so it's here. 1.1, 3.1, 3.2, 0.5, 3.2, 3.4, 2.8, 3.2, 3.4, 3.1, 2.3, 1.7, 2.1, and 1.5. And that's not my final answer for my stem plot, because the last thing I have to do, like the second row, the ones, I would write 1, 1, 5, 7. What did I do? How did I change it?
Oh, you made it in order.
I put it in numerical order. So the next one's going to be 2, 1, 3, 8, and 3, 1, 1, 1, 2, 2, 2, 4, 4. The reason we write it in numerical order is because a lot of times you'll be asked to find the median. And if you remember, the median is the middle number in a list. So if I was listing all of these out in order, then I would say, okay, 0.5 is going to cancel with the 3.4, 1.1 and 3.4. And I go through and I cancel, 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 until I get the middle number, which is 3.1. That would be the median. Does that make sense? So that's why we write it in more order, so we can see the median. Plus, if you have a whole bunch of data values, it's really nice to be able to see like what the mode is, right? What the most is. And it also gives you the nice distribution. So how is this distributed? What kind of shape would this be if I did this? It would be like this, which would be skewed left. They're backwards, aren't they? All right. Do you think that the supermarket wants it to be skewed left? What would you think that they want it to be? Skewed right. They prefer for it to be skewed right, so they would have to make some adjustments. If someone's waiting 4 minutes to get into the line, or like be the person waited on in the line, that's too much. All right, so the next one. So it says the mean is a measure of central tendency, also known as the average. You can denote it in two ways. You can denote it by mu or x bar. So you can read that as mu or x bar. I should have given you more room. So mu looks like an M and a U. It's like this. It's an M, but if you take the tail off, it looks like a U, doesn't it? Exactly. You like my joke? Mu. Jason laughed. I'll take it. All right. Only one person laughed. All right. Yes, that's my mathematical cow. You like him? Mu. I don't know. What should his name be? Bob? That's not a math name. I think it needs to be like Pascal. Do you think Pascal? I think that's a good name. All right. And in order to find the mean, you guys know how to find the mean, right? You know that you add up all of your numbers and divide by the number of numbers you have. It's the average. So if you have n data set numbers, then you add them together and divide by n. Right? So you can see it as x bar. Do you guys like writing x bar, or do you like mu? You don't like the mu? Okay. Depends on what book you're using. It doesn't really matter. All right. Median. So a median is a measure of central tendency that is the middle of a data set when the data values are arranged in ascending order. So the median is in the middle. But if there's two numbers in the middle, what do? We take the average of the two. So if you're canceling the first one, the last one, the second one, the second last, and so on, you get to the middle and there's two, take the average. All right, and the mode is a measure of central tendency that's given to the one that occurs the most, the mode. All right, so we call these measures of central tendency because it's ways to describe the center of data. Some people use these in the wrong way. I'm sure you've seen articles in the newspaper or on websites or whatever that give bad statistics. Okay, that happens. You can use bad statistics. If your mean, median, and mode aren't close to each other, like you can use them in however way you want. What's nice is when your data works out so that the mean, median, and mode are very, very close to each other. That's good. That's good data, right? But bad data that you can manipulate is when they're very, very different from each other. Okay, so here we go. So find the mean, median, and mode of the number of days from mailing to delivery. So I'm going to add up all these numbers. So I'm doing 6 plus 4 plus 3 plus 4 plus 2 plus 5 plus 3 plus 4 plus 5 plus 2 plus 3 plus 4. All right, I get 45. And then I have to divide by the number that are in there. Are there 12? I think it was 12. So 45 divided by 12 gives me 3.75. That is my mean. My median. In order to find the median, I need to write it in order. So my smallest number is 2. I think I made it so it was 2, 2. And then 3, 3, 3. And then 4, 4, 4, 4, 4 fours. And then I just did 5 and 5 and 6. I did it that way so I wouldn't be like, how many 2s are there? How many 3s are there? I knew. 2 2s, 3 3s, 4 4s. All right, so my median, if I'm going through it, I'm like, okay, cancel the first and the last, these two, and so on. When I get to the middle, I have 2 4s. So what's my median? 4, it's just the average of those two. Mode? What do you think? 4. It's the one that's most often. 4. So that's a pretty good data set. All of the things are pretty close to one another, so we can't really like manipulate the data and be like, oh, my average number or the middle number is blah, 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 right? They're all pretty close. It doesn't matter. All right, so there can be several distributions that have the same central tendencies. So all three of these have the same center, so the same median and mode in this case, of 105. Okay, all of them are similar. They have a median and a mode of 10, or a median and a mean of 105. But they're very, very different. If I was graphing these with bar graphs and so on, it's going to look like this. This one's going to be like something like that. And then this one just kind of shoots straight up, and it's like that. Okay, they're very different. Okay, so it's going to be important to talk about the variance. Okay, if you're really spread out, that's not good. So variability. So it says this is the spread of a data set. The second plot has the largest variability because the numbers are very spread out. The third has the smallest because all the numbers are really, really close to the center. Okay, there are three common ways to measure spread: standard deviation, range, and interquartile range. Okay, I didn't write what range is. Range is just the biggest number minus the smallest number. So the range for this first one would be my biggest number, which is 125, minus the smallest number, which is 85. Guys, are you paying any attention to what I'm talking about? All right, so 125 minus 85 is 40. Okay, but this other one would be, the range would be 145 minus 65. This one got a little high. There's the 5. And that's going to be 80. We don't want our range to be really, really huge. We want it to be more clustered in the middle. Okay? All right, deviation. This is a weird thing. Okay, the deviation is just the difference of a data value. So any data value xi, so it could be x1, x2, x3, it doesn't matter. Xi and the mean. So it's going to be xi minus mu, or if you like the x bar, xi minus x bar. Okay, and here's what we're going to use the deviations for. So you guys remember way back in like chapter 2, I had you guys do scatter plots. You remember those? Okay, and we found a line which is called the line of best fit. You can do that with your calculator, but we found it kind of by hand. It wasn't really the line of best fit that I had you guys find. I had you just find like any 2 points and connect them. But there's a way to do it on your calculator to find the very best one. And you can do it by hand too, but it's annoying. All right, so here's what happens. Okay, looking at my scatter plot right there. Everybody looking up at it. Do you guys see? If I have something here that's really far away, let's say that was my deviation was -3 there. It was -3, so it's 3 units below where the line was. You guys understand that? If I square -3, what do I get? 9. Okay, it makes it even worse. So if I take -3 and I square it, it's even further. It's 9 units away. Okay, sometimes you could have, like, maybe this is +3. Sometimes a negative deviation and a positive deviation, when you're adding all these things together, it's going to look like there were no deviations at all. Because if I have -3 plus 3, it works out to be 0. Does that make sense? Do you guys understand what I'm saying? So we want to know what the deviations are. We want to include those. So what we do is we square them. So both of these become 9. Okay, so when I add 9 and 9 together, it's 18. That's big. That's telling me that I'm pretty far away from the actual line of best fit. But what happens if I take something that's really close? So this one right here, let's say it was 1/2 units away. If I take 1/2 and I square it, what does it become? 1/4. Is that better or worse? If I'm saying I'm 1/4 away, is that better than 1/2 or worse? No, it's better. I always give you a 50-50 chance and you always guess the other one. Just go for it. Okay. So yeah, it's 1/4. It's better, right? It seems to be even closer to the line. So when you have something that is far away, like if I had a point that was way up here and it was 7 units away, when I square that, it becomes 49. It is exaggerating how bad it was. Okay, but if I square something that was really close, it's exaggerating how good it was. It's making it even better. Do you understand what I'm saying? So that's the process that statisticians use to find the variance. So, and the standard deviation, which we're going to talk about. So it says positive and negative distances might cancel each other out. So therefore, we square each deviation, which makes them all positive, and then we take the average. This quantity is called the variance. Okay, the standard deviation. The standard deviation is a measure of the variability that describes the average distance of data values from the mean. So we're going to take the average somewhere of all these deviations, so the thing I just talked about right here. Of all the deviations, I'm going to find the average of all of them. The standard deviation is denoted by the lowercase Greek symbol sigma. Do you guys remember sigma, big sigma? Yeah, it's not that one. It's the lowercase one, sigma. It's like an O with a little line there, sigma. And that's where usually people are like, I don't understand. They don't look anything like each other. Why would we do that? I don't know. Why do we do this? Like, they look nothing like each other. What are other letters that are like nothing like each other? E and E. E and E aren't really, yeah, that's kind of like our E and our Q. Q's aren't close, yeah. So don't hate on the sigma, how it's nothing like the other sigma. Yeah, D, it's backwards. All right, so if I put this on your test, I will give you this. I will give you those 5 steps. I will tell you what those are. And you will find it by hand. So it says, luckily, you can input data in a graphing calculator and it will find the standard deviation for you. I'm going to show you how to do this by hand. Okay. I'm not going to give you very many steps. Okay, like very many points. Yes. Close. She's saying, are the deviations 81, 87, and so on? Those are the numbers. Those are my data values. So here's how we do this. So I recognize that my numbers are 81, 87, 92, 94, 96, 97, 101, and 104. Those are the numbers that are listed in the stem plot. You guys agree? You got that down? Okay, but I need to find what I call deviations. Well, I don't call it. The book calls it that. All statistics calls it this. All right, and deviations are how much it's off. So I'm going to subtract out the mean. So first I need to find the mean. So I take all those numbers, I add them together. So I'm doing all that on my calculator. I'm adding them all together. How many numbers do I have? Can you guys count them up? I have 8. So I get 752 divided by 8, which is 94. That's my mean, which makes sense. You're not going to get a mean of like 125 with this list of numbers. You get it? If you're getting a mean of 125, you're doing it wrong. You guys see why it's like 94? It's somewhere in the middle. Right? It makes sense. It's not going to be like 125. All right, so I'm going to take each number minus that standard, or minus the mean. But remember, I told you, sometimes negative numbers and positive numbers cancel each other out, and we don't want that to happen. We want everything to be positive. So what do? We don't make the negatives into positives. We also want to exaggerate anything that was bad and anything good. We squared them, so we're going to square everything. And you can do all of this without a calculator. Don't use your calculator on things that are really easy. Like I have seen people put in 94 minus 94 squared. It's 0. Right? Do the ones you know how to do without a calculator. So like 92 minus 94, that's negative 2 squared. What do we get? 4. How about 96 minus 94? 2 squared. 4. This next one? 9. The next one? 7 squared. What are you doing?
16.
No, 7 squared is 49. All right, and then 10 squared is 100. So if you need your calculator, use your calculator. So if you have an 81 minus 94, 81 minus 94 is negative 13. So I have 169. He's just messing with me over there. All right, 87 minus 94 is going to be negative 7 squared. 49. Okay, those are all of my deviations squared. So I found my deviations and I squared them. So maybe do your little deviation squared. Okay, my standard deviation is going to involve averaging these and taking the square root. So the first thing, when I average them, that's going to be called the variance. So variance we sometimes write as sigma squared. So my variance, when I add it together, 169 plus 49 plus 4 plus 4 plus 9 plus 49 plus 100. I get 384. And then in my instructions it says divide by, take the average of these numbers. So I'm going to divide by the number of numbers I have. So I have 8 numbers. So when I do that, I get 48. Yes?
Where did 384 come from?
I added all these numbers, 169 plus 40. So find the sum of the numbers. All right, but I want the last thing, I want sigma, standard deviation. So what do I do now? Yeah.
Are you just supposed to add them up in your calculator, or are
Yeah.
you supposed to do the way that we did it?
You can add them to your calculator. All right, so I find my standard deviation, which is just sigma, by taking the square root of 48, which I'll write as a decimal. So the square root of 48, 6.928. We'll do 3 decimals. Okay, does that make sense? Yep, just the positive. Okay, so I know that you guys have no idea what a standard deviation is. I remember when I was in school, I was like, what? Why am I finding this number? Why is it important? It is important in stats. Okay. Yeah. Basically what a standard deviation is, you don't have to draw this, but when you have something like the bell curve, you want to know how many standard deviations you are away. Like if you're 1 standard deviation away, so this distance is sigma, and this one's sigma, so you're from the center, you go 1 sigma out on the left as well. That includes 68% of your data. But if you go 2 standard deviations away, 95% of your data is included. Okay, so it's basically telling you what percentage of people fit within those standard deviations. Okay, so it would allow you to find like outliers and so on. And it's also the way that we produce different things. Like, you know, like if I talk about the average height of a male, like it's going to tell me how many pairs of pants I should do that are this high, how many pairs of pants I should do that are this high. You know what I'm saying? Like it's important in real life. All right. So I gave you a little note here. It says there are 2 types of standard deviation. The population standard deviation is what we just found. That's the one that you're going to be doing by hand. Okay, but oftentimes we will use, like if you go into AP Stats, you're going to use the random sampled standard deviation. That's going to be your main standard deviation that you'll use. Because what happens is you survey so many people, such a large random sample, that instead of dividing by 8 here, when we get 384, we instead divide by 7. And I don't know the exact reason we do that. I'll have to ask Maury about it. But I always thought when I was in school that I thought it was because of the outliers. Like you need to adjust for a certain number of outliers. So you divide by n minus 1 instead of n. And then you take the square root. So if you do that, if you do the square root of 384 divided by 7, you end up getting 7.407, which isn't super close to the other one. Usually they are very close. Okay, so usually they are very, very close. The more people you have in your sample, the closer they will be. Okay. All right, and the very last thing's pretty easy. Back when I first started teaching, they still had the I step in 9th grade. You guys don't have to do the I step anymore, but they had that. You guys now have like your Core 40, your end of course assessments that you have to do. But I remember some of my students were like, they asked me this question on the I step about quartiles, and I didn't know what they were talking about. Okay, this is this type of question, so I want to make sure that you guys know what this is, because you will hear this word sometimes. Quartiles. What do you think quart means? Fourths, right? So we're going to divide things into fourths. So it says they're the medians of the lower and upper halves of the data set. So you're going to have a whole bunch of numbers, and you're going to find halfway. You're going to find the median, and then you're going to find halfway and halfway, the medians of those 2 pieces. That's what we're going to do. The distance between those 2, like the first median and the third median, is going to be the interquartile range, the IQR. Okay, so let's do that on this. So it says the interquartile range is the difference between the first and third quartiles, or Q1 minus Q3. It represents the middle 50% of the data. Okay, that's usually like the average population, kind of the middle 50% of people. Okay, so find the interquartile range of the data. So first we need to put everything in order, so help me out with this. Okay, so how many 2s do I have? 2 2s. How many 3s do I have? I think just 2. 2. How many 4s do I have? 1. 5s? 2. 6s? 7. 8.
2.
3.
3.
9s?
1.
2. You guys are terrible at this. All right, are you crossing them out as you're going? You can cross them out. 10s?
0.
No 10s, no 11s. 12? 13? 14? 15. Okay, I think that's what I have. Okay, so I need to find first the median of this data set. Okay, so I'm going to go through here, And I'm going to, basically I'm saying cancel, 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 cancel. Remember, sometimes I do like 3 or 4 at a time. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2. I get 7 and 8 in the middle. Okay, when that happens, so if you have an even number of numbers, you just want to go directly between them and don't include 7 on like both sides or 8 on both sides. If you have an odd number of numbers, you don't include that number in the middle. Okay, you cancel it out. Okay, so like if this was 7.5 was in the middle, you just don't include it on either side. It's just crossed out. Okay, does that make sense? Okay. All right, so we're directly in the middle. Now we're going to go through and we're going to find the Q1 and the Q3, the medians of these two sets. So I have this half and I have this half. So I'm going to find the median. So I 1, 2, 3, 1, 2, 3, 1, 1. So it's 4. You can see that? That is what we call Q1. It represents the end of that first quartile, the first quarter of the data. All right, and then I find Q3. So 1, 2, 3, 4, 1, 2, 3, 4, 9. That's Q3. So remember that's directly in the middle of the other half. The IQR, all it is Q3 minus Q1. So it's 9 minus 4, which is 5. That's your answer. Pretty easy, right? Doesn't take very long. It's what represents the middle 50% of the data. Okay, so if I ever want to know, like, we're producing T-shirts for the school. 50% of the people would wear these sizes, right? That makes sense. Middle 50%, and then you would order the other outliers that you need.